In this problem, a horizontal spring is attached to a wall. An 8.5 kilogram mass is slid across a frictionless horizontal surface at 2.8 meters per second. When the mass hits the spring compresses 45 centimeters. If the surface is 1.4 meters above the ground, find the spring constant. I've tried to model this situation up here in this series of diagrams. We have a table that is 1.4 meters above the ground, and the table is next to a wall, and we have a spring attached to the wall with a little catch end for the spring, and we have a mass that's sliding across this nearly frictionless surface with an initial speed of 2.8 meters per second. The mass will of course hit the spring, causing the spring to compress, and that's what we see on the right. We're told the distance the spring compresses, and the question is, what's the spring constant? On the left we have snapshot A, and on the right we have snapshot B. Let's look at snapshot A first. The system involves some kinetic energy in snapshot A, namely 1/2 times this mass times its speed squared. 1/2 times 8.5 times 2.8 squared. To calculate the gravitational potential energy, we have to define a reference line. And remember that the reference line is arbitrary. We can define it wherever we wish. I'm going to define the reference line as the tabletop. And that's because the height of this mass above the tabletop is 0. So there is no gravitational potential energy in snapshot A, and as we'll find in a minute, there is also no gravitational potential energy in snapshot B, if we choose that as the reference line. Incidentally, if we had chosen the floor as the reference line, then the amount of gravitational potential energy in snapshot A would be 8.5 times G, which is 9.81, times 1.4. And it would be that exact same product in snapshot B, so it doesn't matter where you choose the reference line. Back to snapshot A. The spring is still relaxed at this point, so there's no elastic energy stored in the spring. In snapshot B, the mass has slammed into the spring, and the spring has compressed. Now when the spring is compressing, the mass is slowing down, slowing down, slowing down, slowing down, and at maximum compression, that mass for an instant is not moving. So it has no kinetic energy. So that term is 0. We talked about how there will be no gravitational potential energy, but there certainly will be, in snapshot B, some elastic potential energy stored in that spring, equal to 1/2 times the spring constant times the amount of compression squared. So let's add up the term on the left, add those up on the right, set them equal to each other, divide both sides by 0.10125, and find the spring constant to be equal to 330 newtons per meter. Let's try this one. An arrow of unknown mass is launched at an unknown angle with initial speed 45 meters per second. At the top of its path, its speed is 35 meters per second. How high does the arrow fly? It seems like we're not given a whole lot of information here, but let's just go with what we have. How high the arrow flies must depend on us having a reference line. So let's call the elevation at which the arrow was launched the reference line. The launching conditions we'll call snapshot A, and the conditions at the top we'll call snapshot B. The chart that we've been filling out for these problems is simply a tool for the mind to help us understand what we're doing. It isn't necessary in order to solve conservation of mechanical energy problems. So instead, this time, let's just think our way through it. The arrow is going to have kinetic energy here in snapshot A, equal to 1/2 times its mass times its speed squared. Now we don't know what its mass is, so we'll just put m for that. It has no gravitational potential energy because it's at the reference line, and we don't have any springs. So The kinetic energy, 1/2 m times 45 squared, is all the mechanical energy this arrow has in snapshot A. In snapshot B, it has some kinetic energy equal to 1/2 times m times 35 squared, but it also has now some gravitational potential energy equal to m times g times h. Those two quantities of mechanical energy must be equal to each other. As you can see here, the mass is irrelevant, and we can simplify the left side of the equation and simplify the right side of the equation. And now we just need to solve for h. Let's subtract 612.5 from each side, divide both sides by 9.81, and we get that the arrow flew to a height of 41 meters. At what angle was the arrow launched? Well, let's redraw this situation. It has a launch speed of 45 meters per second at some angle above horizontal, and at the top we're told that it's traveling at 35 meters per second. Recall that at the top, the only velocity at the top is the x velocity, the horizontal velocity. X, or horizontal velocity, is constant throughout the motion, which means we know this leg of the right triangle and essentially the hypotenuse. So isn't it true that theta would be the inverse cosine of 35 over 45? That angle turns out to be 39 degrees. Here we went through a few more problems involving the conservation of mechanical energy. Now, while energy is always conserved, mechanical energy is conserved only when there is no friction or other heat losses. If there is friction, we can't use the algorithm we used here. One way to tackle problems involving friction is to use the work kinetic energy theorem, which is a topic for subsequent lessons.